Ramadan Mubarak. I got a request from our partner in Egypt to do a recording for Ramadan contest from Primegear Academy to increase the knowledge on the turbo machinery oil analysis, and hoping that you will be applying for it and you will answer the questions after looking at the video which I am making for you. Let me start with the introduction of EPT Clean Oil. EPT Clean Oil in Canada started 30 years ago by invention of a filtration technology for turbine lubricants, as well as fire-resistant fluids used in the hydraulic systems of turbines. This technology is called ion exchange fluid treatment. Ion exchange resins has been first developed by EPT Clean Oil for cleaning the lubricants. And we have 30 years of experience delivering a lot of success stories around the globe with proven savings on the largest gas turbines and steam turbines around the world. EPT developed products and services as well as advanced the knowledge of lubrication management in the turbo machinery area. And then we needed oil analysis to prove the results we are delivering to clients. So we developed our own fluid technical center like 25 years ago. As well, we advanced the knowledge on lubricant management in this area. Uh, my name is Khashayar Hajiahmad. I worked for 15 years so far. Out of that, it was 10 years for SKF Group. And nowadays, I am working for EPT Clean Oil as the business development manager for Middle East and Africa and East Europe. I am a lubrication specialist, and I will be with you today for around half an hour. The discussion today is discussion about oil analysis for turbines and compressors for turbo machinery. We define what we need to achieve when we are developing a oil analysis program for our turbo machinery. What are the questions we need to ask, and what are the answers we need to get from this oil analysis report? At the end, I am going to share some success cases and some of the case studies that we supported our customers in EPT Clean Oil. So let us start the technical topic. The every oil analysis lab out there is providing you a package of tests, which they are doing for your turbine, for your compressor, and the third-party labs, when we are sending them the samples, they generate money based on more number of samples and more number of tests, and they provide you generally a package of tests that you need to do, and then generally these commercial labs, they have algorithms developed by computers which they feed the results, and then they get some diagnosis that some results are off spec and outside of spec specifications. And then this is, the report is generated automatically, and then if the lab is professional, you will have an expert writing some recommendations, but finally it comes to your desk, and then you need to interpret results, and you need to know the answers. You need to know what to do with your oil. But generally, what we have seen in the industry, these results or these oil analysis reports generally generate more questions than providing the answers. So today, in this presentation, I am going to help you to know what tests to run on your turbine, on your compressor, and on your hydraulic systems of your critical assets, how to understand your reports, what are the important tests to do, and then, for example, for some tests like acid number, there are different methods of testing, so to know the differences. And then what are the limits that we need to be careful about them? I mean, how much increase is acceptable? And, what are the limits? What are the targets in these oil analysis tests that we are going to do? And then, you know, some of the time we are doing the testing, the results are off spec, but how much is the importance of each test? How we decide when to change the oil and when to apply filtration, which test is more important? We call it triaging these problems that they come together. And then what could be the corrective action if you have a high varnish potential, if you have a high acid number, if you have a demulsibility issues, what can we do? So we try to give in this half an hour, 45 minutes presentation, some corrective actions as well when we are defining what to do, what to test, and when to test. And then after getting the results, some actions are important. So let's go with the where to start. I mean, the first thing is that which test to do. I mean, you get a lot of tests. These are some test packages that we received from the very known lab in Canada. That these are too many tests offered and different packages for a known application like a turbine oil. And then the more number of tests, the more money the commercial lab is generating. So it's our decision to make a decision which test to do and when to do, and then to do some diagnosis. So generally, the best source of recommendations comes from ASTM International. ASTM International is a global authority for oil analysis test methods, and it is outdating, or it is older than all the other international organizations in this field. And generally, following ASTM recommendations published in the standards is the best source to go and look for the first time. I mean, the most important, let's say. And here we are introducing to you the three standards that covers most of your plant oils. The D4378-20, the dash 20 means that the year 2020, it was the latest version published, the latest update. It covers the gas turbine and steam turbine lube oils. ASTM D8323, it was published recently for the fire-resistant fluids used in electro-hydraulic control system fluids, and then other plant oils like gear oils and other oils which are not covered with the gas turbine, steam turbine, mineral fluids, with the fire-resistant fluids which are phosphate ester. Those are the other two standards. Other than those two applications, the other oils are recommended how to maintain them, how to do condition monitoring in D6224. So ASTM International is providing them very accessible. They are very cheap, and they are very cost effective, and they provide you the recommendations which they come from turbine manufacturers, from oil analysis labs, from lubricant manufacturers, are sitting and reaching an agreement when they are publishing these documents. So it's a very good source to start with. And then in this standard, generally, you get recommended tests that you need to do, which every STM test behind the is mentioned over there. And then recommended frequency is very important. When to do it? I mean, how long, how much we need to wait to do the test, and then during the year, how many times we should do it. It's very important. And then recommended warranty, recommended warning and action limits. The warning and action limits per test is very important to know, to have a guideline, because some labs are setting the limits for us, but it's very important that we know our warning and action limits based on ASTM standard. And then even ASTM standard is providing some corrective actions in terms of high MPC, high varnish potential, high acid number, high water levels, demulsibility issues. There are some good recommendations in the standard as well, which I really recommend you to have a look. Today we will be covering some of those highlights and most important parts of the ASTM standards. So when you receive an oil analysis lab report, what you need to look, I mean, what answers you should receive from this lab report. I mean, which questions we need to ask ourselves, and then what answers we should receive. So if a turbine oil is in front of us and then turbine oil analysis, we need to first look at this oil is able to do its job, because the function is sometime it is doing the cooling of the bearings, lubricating the bearings. It could be the same oil is doing the function of as a EHC fluid as well. So is it doing the right job in the hydraulic system as well? So we need to look at the physical properties here. The viscosity is the most important part. And then there are other tests as well regarding the physical properties of the lubricant. So first thing is that, is the oil doing its job? Second question is, could an immediate failure occur? You know, what are the contaminants? Are they coming from outside? Are they generated inside? Is there any wear happening? So we need to look at the different tests like ISO particle count, like elemental analysis, and then we need to look into what contaminants are entering my system, what is the water level, where is it coming from. So different failure, different contaminants, they cause different failures. So we need to look at the contamination available in our oil, and then everybody is interested to know how long I can use my oil, how long I can use it. I mean, is there any breakdown very close to me? And then there are certain tests that we can know the remaining useful life of the lubricant. So then the one of the most important tests in that area is the oxidation related tests. So the more oxidation, the more the oil goes to the end of the life. So that is very important to get the answer from oil analysis report. And then we have tests which are really looking into the additive levels remaining, looking the remaining useful life of the oil. So how long will the oil last? This is the question that we need to ask, and we need to get the answer, especially in turbo machinery oils, which are having a large amount of oil and the downtime is causing millions. These are very important questions to ask and get the answer from the oil analysis report. So the first question was, will this oil do its job? The first most important property of any lubricant or of any oil is the oil viscosity. And then if the viscosity is too low, it is causing metal-to-metal contact, inadequate lubrication is happening, a lot of wear. So we need to monitor the decrease in viscosity. There could be a mix of different lubricants together, which decreases the viscosity. There could be a thermal degradation in the initial stages. It will be cracking the oil structure and decreasing the viscosity. So we need to think about it, how much is acceptable. Generally, the industry and standard mentioned also in ASTM standard is recommended limit is plus and minus 10%. So the drop of a 10% is not is too much, and more than that is not acceptable. The increase of viscosity as well causes problems. You know, generally lubricants which are oxidizing, you will have increase of viscosity of the lubricant, but how much is acceptable? We have here as well a 10% limit. The high viscosity causes internal fluid friction, so you will have friction happening inside the fluid. It will be causing heat, and then finally the heat will be causing the oxidation, as well as the drop of viscosity is the end result. When even the high where viscosity is first stage is going high, and then the problems start, and then you will have even very, very high frictions overcoming that viscosity, which is increased. So we need to, generally, we have seen very few cases that the viscosity is increasing to the high levels of 10%, but generally with the very, very unfortunate cases of mixing different lubricants, which, like we call it, I mean, wrong type of lubricants are added together, or lubricant is not topped up or filtered for a very long time, you will have viscosity issues, which these normally cannot be fixed. We need to change the lubricant if there is any high decrease or increase of viscosity. Then we ask a question, could an immediate failure occur? We need to look at the contaminants here. The contaminants are the ones which are harming the system, and then we are going to measure them in oil analysis lab tests, which are developed for that purpose. So we look at the particles here. The particles can be generated from the internal mechanical components. They can come from outside, the solids from outside, for passing through the seals, coming through the oil. So we need to count them to know the numbers and to know the how many are available. And then here, count the water level. What are the water content in my lubricant is very important. Water damages the lubricant in many different forms and many different pathways. It damages the base oil. It makes more consumption of additives. It increases the oxidation rate. So we need to look at the water level. The oil should be as dry as possible, and there are different tests for it, which I am going to talk about it. And then we need to count the metals. Some metals are related to additives. Some are related to the contaminants. So we want to know the contaminants or the additives. Are they present, and how much they are, and what is the source of it? So we are doing elemental analysis when counting metals to know the sources, to do the right root cause failure analysis. So talking about the insolubles and talking about the particles, we have a test, we call it ISO particle count, that we are counting the number of particles and sorting the sizes available in our oil. It's very important to know between your journal bearing surfaces, in your hydraulic systems, the number of particles. And then the narrower the clearances in the system, the problems are more when you have more particles in the system. It will be causing the damage more where you have less clearances. So let us see how we count them. ISO particle count is very known. We call it ISO cleanliness code as well. So this is a 3-digit code. The first number is counting as per a standard, the number of particles more than 4 microns. So it's a class. It's a number indicating the numbers of particles more than 4 micron. Second number is showing the number of particles more than 6 micron. And then the third one is showing the bigger particles, which are more than 14 micron in size. The issue with ISO cleanliness code is that people tend to keep it not very important, but we need to understand that every digit going higher with the first, with or second or third ISO particle count code, it means you have 2 times more particle in that range. So if the first number is 18 and then you have an increase to 19, so it means you have double the particles bigger than 4 micron is double. So this is a little exponential value, and we need to be a little bit careful with the numbers. And every also code is important for 6 and 14. The third is the more damaging part. The first code is showing the small particles which are starting up of the wear or the ingress of contaminants in the system. So we need to really care about each code here. The guidance we have provided to you, ASTM D4378 and D8323, they are providing the limit based on the application. D4378 was a lube oil application, mineral oils in the gas turbines, steam turbines. So it is giving you a limit of 18, 16, 13 maximum. So this is the limit, and we should not run dirtier than this. This is the maximum number of particles allowed in this application. And look at the A323. It's coming down to 16, 14, 11, which means in electro-hydraulic control systems of turbines where we have servo valves, the cleanliness is much more important and the number of particles allowed is less. And then look at the right-hand side of the slide. I will try to show it to you via my pointer here. This is an oil analysis lab report from a turbine application. And look at the results here. We are putting the target here as a 16, 14, 10. And then the customer is running its hydraulic fluid with a 25, 22, and 11. So 11 is, as per DA323, is within the target. So the 11, the bigger particles, bigger than 14 micron, they are keeping them below 11, like 11, which is a good one. But 25 and 22 are much very high, and they're out of scope, out of the specifications. Look at the 25, is 512 times worse than 16. So 2 to the power of 9 here. So, and then the 22, the second digit, is 264 times worse than 14. So you have a 2 to the power of 8 here, which is the higher than what it should be. So we need to keep every digit in ISO particle count within the specification. It seems in the site here, the filter elements or the existing maintenance they are doing, the existing filtration is removing the bigger particles, but they are not able to remove the smaller particles and within the ranges of small particles. So they are having damages of the damage from these smaller particles in their system. We need to keep the 3 digits or the 3 numbers in ISO particle count, all of them within the specification, which is 16, 14, 11 for hydraulic applications, 18, 16, 13 for lube oil application. And then if we are out of a specification, what are the actions that we need to do? We need to upgrade the filter elements on site with the inline filters. If the inline filters cannot be upgraded or cannot be improved with their sizing, with their beta ratio, we cannot achieve the target cleanliness, then we can apply a filter cart. We can apply an offline filtration unit, a kidney loop system that it will be permanently installed on the tank and then cleaning all the time, achieving the targets of cleanliness all the time. This is what we do normally when the inline filters are unable to provide the targets we need. And then let us go to the water level, which is very important for specifically for steam turbine application, because in gas turbine application, we have more problems of temperature, more problems of oxidation. In steam turbines, we have sometimes steam leaking from the seals to the oil. And then while we have a steam leakage, we can have a water ingress to our lubricant, and then lube oils in turbine applications or even in EHC fluids where we have esters, they are not very happy to receive water. When the water comes inside, we have first water as the dissolved format, and then the water increases. Then we have emulsified water, and then once we have more water inside, then we will have a free water in the system. You see a lubrication system from a turbine, and you see corrosion marks here. This seems to be that the water level was not managed, and you had a free water in the system. It causes corrosion, and this corrosion damages the oil, damages the mechanical parts. So the oil and water, they don't like to be mixing together. You know, it generates a lot of problem, wear, failure, corrosion, breakdown. So how we measure water in oil is by different methods. The first method here mentioned is Carl Fisher, shown by KF, which is the most precise method of measuring water in oils. And then we have relative humidity sensors, which are possible to be used on site. They have some errors, but they are good for monitoring and trending the water levels. We can use in the lab the test called FTIR. FTIR tests are not having a very good repeatability, and they are not very accurate in terms of showing the water level. They are very cheap tests to do, very cost effective, show number of results when labs, they like to do it because it's very fast, but it's not showing the very precisely the water levels when the water level is very low. So we don't really recommend FTIR for calculating the water levels. And also there is an on-site test for high water levels of like more than 700, 800 ppm, more than 1000 ppm, we do crackle test, which is a hot plate test. We put an oil sample on a hot plate with 150 degrees centigrade temperature. So it will start to make noise, and it will the bubbles of the oil, the water in the oil will start to be collapsing and creating some noise. That it is showing the water presence. So that's also not a very accurate test, but it's a very good test on site when you have the oil is looking milky, and you want to make sure that this is not a foaming issue, this is a water issue. So you can put it on a hot plate, and then just make sure on site that you have a high water level ingress. But the best method that we recommend in EPT is called Fisher, that that doesn't have any repeatability problem, and the error is not high. It's showing very accurately the water level. So regarding the water level, depending on if your oil is mineral oil or your oil is a synthetic oil, like ester oils used in the phosphate ester oils used in the EHC systems of turbines, they are absorbing water from the air around them, and they can accept more level of water inside. But even the higher levels, it will damage these ester-based oils. So we need to keep it between 300 and 500 ppm. So we need to have a method of removing the water slowly from these ester-based lubricants as well. So we don't need to let them have a lot of water to damage these very expensive fluids. And then for mineral oils, the maximum now allowed water level is 200 ppm. More than 200, you will have a very fast emulsified water, which will be damaging your lubricant film, and it's not allowed to operate higher than 200 ppm. And then regarding if the water is ingressing your lubricant, and you are sure by testing, there are different methods: centrifuges, coalescers, vacuum dehydrators. They are tools available to fix and to remove water from your lubricant. And in EPT, we have a very good experience of putting a dry gas blanket on top of your oil. What does it mean? It means that we take from a compressed air source, we have a machine called TMRN2 that we separate the nitrogen, and then we put nitrogen, in Arabic we call it azot. So we put nitrogen gas on top of the lubricant in the reservoir, and then we absorb the water from the lubricant. And then by this method, we are doing water removal slowly, because of the balance between dry gas and also the lubricant. It will be removing water slowly from lubricant. And as well, by this method, we are removing oxygen from the top of the reservoir. So we are decreasing the oxidation rate of lubricant as well. I recommend having a look at our website. There is a very good presentation on oil and water mixing issues and emulsibility issues that my colleague, who is an award winner from ASTM, Dr. Matthew Hobbs, is presenting on this subject. It's a very useful presentation. Coming to the metals, we are doing elemental analysis to count which metals are present in my oil. Are they coming from where, like iron, copper, chromium, and other metals, which are rare metals available in the alloys of bearings and in the surfaces of the system, in the tank, and so on. Wherever the oil is in touch, these rare metals, they can be captured and brought to the oil sample. We can test for them. Then there are some additives in the oil, which they are from having some source of metals like calcium, magnesium, zinc, and so on. So these can be monitored, and then the additive consumption can be monitored with counting these metals. And then D4378 provides a complete list of these metals and their source. I really recommend looking at that good resource when you are doing an elemental analysis report testing, and when you're looking at the report. You know, the consequences of having a lot of metals, these are showing the acceleration of the breakdown of lubricant. These metals, they promote deposits and varnish and gel in the system, And then the wear metals also, if they are big, they will be contributing to the wear of bearings and other mechanical components like hydraulic systems. So we need to bring down the wear metals and also minimize the additive consumption in the lubricant, which we can monitor it with the elemental analysis. It's very important. If we see the contamination inside, we can pull these metals outside. With ion exchange method filtration of EPT, we pull the metals outside so they don't cause damage, but it doesn't fix the source. So we need to pull them out, but at the same time, we need to look at the source which is generating. And then looking at is the failure going to happen soon or not? If the main pathway of failure of lubricants is oxidation, and then the oxidation is the reaction of lubricant with the air molecules with oxygen, and it is causing acids, it's causing oxidation breakdown products in the lubricant. And then once the oil is saturated from these material, it will be creating deposits in the system, which we call it varnish. So how the oil is breaking down, how much is going to last my oil? It's very important to measure acids which are produced by the lubricant. The acids makes the environment corrosive. It promotes the acidic wear in the metals in the system. It generates deposits finally. The lubricant, which is having a high acid number, finally these acids are varnish precursors or starting up the reactions which they will be finally causing the lubricant to be saturated from these molecules, and then it will be starting generation of solid in the system. So the sources of generation of acids in the lubricants are oxidation. Generally, we have weak organic acids produced by mineral oils, and then on the ester side, which we have it in the phosphate ester in the EHC fluids, the hydrolysis, which is the reaction with water, they cause strong acids. So the phosphate esters produce strong acids, which we need to be careful between strong acids and weak acids. Most of the people, they are doing only total acid number, which is the acid number coming from weak and strong acids. But there is an SAN number as well, which is focusing on the strong acids in the lubricant, and we can separate it for you within the test we are doing. So there are different tests to do for knowing the acid number of the lubricant. The D664, we recommend to do this method. This is called a potentiometric method. Actually, with this method, we are using a reliable method, not based on a human sense like D974. It's a visual method, so based on a reaction which happens with the fluid, there is a change of color, and then it's completely done by a human, and reporting the acid number and total acid number is done by human. But in the 664, it is done by the machine, and then we are just calculating the acid number, and it can also report the strong acid number as well. So the 664 potentiometric method is much more reliable in terms of reporting acid number, and also if you want to do different, if you want to monitor and do the trending, it's much more stable to do with the D664. Generally, we should not change. We should not compare the different results coming from different test methods. If a lab is doing 664 and the other lab is doing 974, we should not compare these results. And then the ASTM recommendation is coming that for the oils, for the turbine oils, having a less than 20,000 hours life, a 0.1 increase in acid number, yearly 0.1 increase is acceptable. And for the more aged oils, which they have a higher than 20,000 hour oil life, a 0.15 increase in acid number is acceptable. This is very logical because your increase of acid number depends on your oil life. and the more consumption of antioxidant additives. The more you have antioxidant additives lost, you will have more increase of acid number year by year. So this is completely logical, but to be honest with you, if you have a 0.9 increase of acid number, as per ASTM D4378, is a good one, but we don't really recommend a 0.9 increase over a year. It's too much. So just take it as an indication here. We recommend in EPT putting the acid number of a new oil, and generally the rule of thumb is the more than 2 times of acid number of a new oil is considered to meet the limit, and then we should not cross that limit. And then with the D8323 for a phosphate ester fluid is very easy. It's a 0.2 maximum, and we should not cross a 0.2. This is also a good recommendation coming from this new standard. So it makes it very easy for managing these phosphate ester fluids. And then for fixing acid number, the only filtration technology is ion exchange resins of EPT, ICB, which has been developed to remove acids, strong acids, as well as the weak acids. For different fluids, we have developed different resins to remove acids from the oils, and then by changing ICB as much as required. For example, if you have an oil of outside of a specification, within the first month we change the filter, within the second month and third month, maximum in 3 months, we can fix the acid number issue with mineral fluids. But depends on how much you are out of a specification. Sometimes we need a lot of ICB filters from EPT to fix the acid number. The starting acid number is very important, how much we are out of scope. But we can still fix the acid number and then reduce the antioxidant consumption with the ICB filters from EPT, which the mechanical filters are not able to do this for you. I mean, the mechanical filters or deep filters, they don't correct acid numbers. Then we come to the varnish. Varnish is the most common cause of gas turbine oil related downtime. You know, it is from a document coming from GE. Most of the gas turbines in their life will be suffering from varnish. And then shall we wait for this to happen, or we can have a more proactive way of maintaining these lubricants? So these lubricants are oxidizing. The oxidation material is first dissolved in the oil, and then once the oil is saturated from this material, they start to produce deposits. These deposits are called varnish. They cause valve sticking, they cause filter plugging, high temperature operation of bearings, and the lube oil itself, and then the equipment wear can happen when the deposits are bigger than the clearances of the system. The wear is going to happen. The cooler performance also has a problem, because in the piping you will have a layer of varnish in the system. You will have a cooler performance issue because of the heat transfer will have a problem. So the most important test is the D783, and then it is updated the year 2021. I will talk about the update. In this test, we are preparing the oil. We are heating the oil for 1 day at 60 degrees, and then 3 days at the dark area. We are keeping it so the soluble varnish and insoluble varnish, both they come out after mixing with the solvent, which is a non-polar solvent, and then the result, the oil is filtered on a 0.45 micron patch, and then the stain on this filtration job is done. The stain on the filter, which is a 0.45 micron patch, it is showing how much soluble and insoluble varnish was in the oil. And then the darker the patch, the more your oil was having oxidation material, the more oil was or saturated inside your lubricant. Remember, we condition monitoring people, we have worked a lot with vibration. This is not a vibration value that you care about. The number in vibrations is showing the displacement, the velocity, and the acceleration. Here we are checking a lubricant oxidation rate and also how much it is saturated. So the color intensity value coming from varnish potential test, which is shown here, we use a spectrophotometer, we check the color intensity of the fluid color. And then MPC values, the color intensity values, which are shown here, MPC below 15 is considered good. The 15 to 35 is considered elevated varnish, and then above 35 is considered high and risky critical varnish potential. Let us focus on the word potential. Here we are checking a fluid sample. Does it mean that the MPC of 14, your oil doesn't have a problem of varnish? No. MPC 14 means that it is still saturated. There is a stain, but it is not very, very highly saturated. So let us keep these in our mind that delta E and varnish potential should be minimized close to zero as much as possible. So this is a risk value. So you don't want to say that if your varnish potential is 14 and 13, you don't have any risk. No, there is a risk. There is a still high risk of having varnish in the system. This is a case also that we are showing that some people, they don't do the varnish potential test as per ASTM method. This shows that the top oil has not been done as per the guideline in the ASTM test. Is showing MPC of 3, and then the right test with the right heating, right incubation has been done, MPC is 22. So because soluble varnish from the oil, it should come out, and then we are having that incubation period that the soluble varnish will come out during that 3 days of staying in the dark area. So we are taking out the soluble and insoluble varnish together in this preparation of this lubricant during the ASTM test. The D4378 and also 8323, with the latest update, they are mentioning the delta E or the varnish potential above 20 is a warning, and above 13 is an action point. But we remember that we should keep it below 5, close to 0 all the time. And then there is an update with the varnish potential testing. You know, the hydraulic oils, they can have problems of micro dieseling, and as well as we can have electrostatic discharges in the filter element. Micro dieseling is the bubbles of air trapped in the oil. When they go on high pressure zones, they collapse, and they are cooking the oil with the high temperature event. You will have the hydrocarbon, it will be breaking down to its carbon component, and then you see black carbon because of these high temperature events. Sometime in the filter elements, we have sparks as well. We call it electrostatic discharge. And then this black carbon is not varnish. So in the varnish potential test, if the lab is not expert and is not having the knowledge, it will be putting the spectrometer on top of it, reporting a high varnish potential. But this is not varnish. The black carbon is coming from other issues. The brown patch is the normal oxidation, which is coming from the oxidation process, and varnish is forming. So with the latest ASTM standard update for varnish potential testing in hydraulic systems, especially for phosphate ester fluids, we are reporting delta L and delta A plus B, which are the color contributors in the varnish potential test separately. And then you see high delta A plus B, it is those color contributors for making it brownish, and then high L value is showing how much black and black is our sample. So delta L is the black carbon, which should be treated with like electrostatic contamination removal methods, which are the best method to remove. These are sub-micron in size particles. And then delta A plus B is showing how much is the varnish potential, how much is the oxidation, and the brownish color. So we need to treat delta A plus B with the ion exchange resins from EPT, ICB. And then delta L is the problem that it will be best treated with electrostatic contamination removal. So that's the reason EPT has come up with a solution integrating two filtration technologies called ion exchange resins, ICB, plus ECR. ECR is the electrostatic contamination removal to remove the delta L, the black carbon in the hydraulic fluid. And then the machine called soluble varnish removal, SVR, from EPT will keep the varnish potential minimum all the time. We don't allow the oil to get saturated from varnish molecules. And then while you keep your varnish potential below 5 all the time, it is very good that you are removing the oxidation material all the time. So antioxidant package will be remaining safe for many years, and you are increasing the life of your lubricant as well. So you are mitigating the risk, and then no problem happens regarding varnish. So then regarding how much my oil will last, we need to know the additive levels. As per ASTM standard, once additive, the main additive which is used in the oil, in the turbine oils, or let's call them R&O oils, rust and oxidation inhibited oils, they are the antioxidant additives. And then generally antioxidant additives, when they reach to 25%, there is a huge increase of acid number as well at the same time. So we need to monitor the additives. They don't drop below 25%. And then this is showing us how much is the remaining useful life of lubricant as well. There has been tests developed by the lubricant industry called D2272. We call it a rotating pressure vessel oxidation test, RPVOT, which is measuring the lubricant remaining oxidation life. So it is putting the lubricant under stress, putting some contaminants inside, and then measuring the remaining useful life of lubricant, based on oxidation. And then there is another test called linear sweep voltammetry, D6971. The machine was named Ruler when this test was invented. This test directly measures the amine or phenol, which is formulated as the antioxidant in a turbine or compressor lubricant. So it's a very much more the detailed test that it is measuring only antioxidants. So RPVOT is also based on base oil as well, and the whole formulation of the lubricant is under stress. But once we are measuring the antioxidant directly, it's giving us a better indication that how much antioxidant we are losing per year. Generally, we need to minimize the lubricant additive consumption, the antioxidant consumption per year, so we can have a less risk of varnish and then high acid numbers at the end. We need to be a little bit careful with the LSV results, because these tests are not very repeatable. So it could be that you test this month, you have 80% left. Next month, you get a 90%. The other month, you get a 75%. So the more important is the trend after 2-3 tests that you do, then they are downwards. So look at the trend. Don't look at each result. I mean, you can repeat the test for the same oil and you get different results. If you are doing it at the same time, I mean, then just focus on the trend on these tests. And then the best way of maintaining a lubricant in these critical assets is to treat them with the SVR and ICB from EPT, bring down the acid numbers, bring down the varnish potential to the minimum, and do a, like, let's say maximum 5% top up of the oil to bring up all the additives required to do the job. With the full-time treatment, we never allow the acid number to raise, the varnish potential to raise, and then we are increasing the life of lubricant as well. People wait for varnish to come and then to start to treat it. That can be done as well, but once you put the oil full 24/7 in this turbo machinery, full-time treated with ion exchange resins from EPT, then you achieve excellent results. The life of the oil will be like 25 years has been achieved with an EPT. And then a summary of what I have discussed. Look at the different results in your lube oil analysis results. Look at the viscosity, which is the most important parameter. If you want to know if a failure is coming, look at the particles, look at the water level, look at the metals. If a failure is on the way, look at the acid number or varnish potential. And then if you want to know how much your oil will last, look at the linear sweep voltammetry and RPVOT results. So this was a summary of what I discussed so far. I collected some of the case studies that I have done in my career with EPT. This is a Siemens gas turbine, that V94.2, which you see a huge amount of varnish in the tank. This happened after 3 to 4 years of using the lubricant, and then MPC was above 35 here or 40, and then huge problems happened. People, they see varnish and they feel that, okay, we do flushing and we change the lubricant. By just charging the new lubricant, you are absorbing back the existing varnish in the system to the new lubricant, and you are damaging the antioxidant package. This is also a GE frame 9, a middle bearing, which a deep filtration method was used, the depth filtration method. The depth filtration method had a lot of filter consumption as well. There was an improvement on MPC. There was an improvement on acid on the particle count, but the oil was still saturated. After some years, again, the varnish potential started to raise, and again, the problem of varnish started to happen. So these technologies generally, they improve the situation, but they don't remove the root cause of the failure. This is again another Siemens turbine, which I was working on it, and then high varnish. You see how it is accumulating at the surfaces. This is also SGT 800 from Siemens that you have it on the lube oil system. Lube oil system is generally left alone in these type of turbines with the inline filters, and you see it a huge varnish in the lube oil and as well as on the gear set. Generally, hydraulic systems in these turbines are kept a little bit more under sophisticated filtration methods. The lube oil system is left alone, thinking that varnish is not a problem in lube oil, but it is also a very big problematic in the lube oil application as well. This is a case study that we have done, baseload gas turbine. After 9 years, the MPC value, varnish potential, never increased more than 1.8. Look at the ISO particle counts. This oil was full-time treatment happened with SVR, with the soluble varnish removal machine from EPT. We have two technologies in this machine. ICB filters to remove acids. Look at the acid number, 0.03, which is better than a new oil even. And then look at the MPC values, and then we have also a second filtration method, which is a very fine filter, mechanical filter, to achieve the right ISO particle counts. And the good results is with the linear sweep voltammetry results, ruler test results, which after 10 years of using this lubricant, just with 5% top-up per year, still only 8% of additive is lost. So this oil can easily be moving forward with 25 years of life without any problem, just with 5% top-up per year. We don't add any chemicals to the oil as well. No need of adding any chemicals to the oil, or we just recommend adding the same oil just to top up the same oil. This is a GE Frame 9 that I worked with it in Oman. It was having a very high varnish potential at the start. And you see 45, high ISO particle count, 24, 23, 16, and a 0.1 acid number. And then we treated the oil, we're using the APT machine, and then you see after 3 months, we achieved the results as per the ISTM standard. And this oil was staying there up to now, which is 2022, with 6 years. Same results has been achieved yearly with just 5% top up and yearly ICB filter replacements from EPT. This is a global success story for APT with a combined cycle facility with 2 units, 600 megawatt turbine, and you see within this steam turbine there's a 600 liter reservoir for the EHC fluid. It's a electrohydraulic control system fluid, and then the oil analysis report is showing a 16, 14, 10, which is a good one. But we in EPT, we check the patch weight as well. The patch weight is very high. We applied the two technologies, ECR, electrostatic contamination removal, to remove the carbon. And then we applied ICB to achieve the right MPC values, the right varnish potential values. And then look at the results. The patch weight within just 3 months, it was reduced to 98%. MPC, very great results, and also the from 63 MPC we achieved 10.5. So two technologies at the same time to treat the two different mechanisms of failure in this application. And then we have a nuclear facility, which is a very large one. EPT has done a great job over there with the hydraulic system. You see that the ECR, ICB, and then water removal system from EPT, the TMRN2, the nitrogen generator, has been applied to the oil, and then we achieved the great results of both the patch weight, the MPC, and then the water content has been reduced a lot. This is a great result, applying the three technologies together to apply the water removal system, ion exchange resins, from EPT and electrostatic contamination removal, especially on hydraulic applications. Just the last point to discuss with you. Turbo machinery are very critical, and then EPT is the most knowledgeable company in the area of turbo machinery oil maintenance. You can come to Primegear Academy, and you can come to Atlasco in Egypt, who is your partner over there. We can share with you our knowledge and then help you with turbo machinery oil maintenance. Thank you very much for supporting and then attending this webinar, or let's say this recording for Ramadan. I would say Ramadan Mubarak to all of you and wishing you the best. Hoping to see you. Bye bye.